what we call a factor valued functions. All right. So remember in the very beginning of Math1A, we discussed a little bit about input-output system. So this is a process. Here's you have an input and you have an output. Okay. And this one is the simplest one. Single input and single output. Okay. More complicated one has number of inputs. X1, X2 to Xn, and one output. Or the other one has a single input, but multiple output. And of course, the most complicated one is the more general one is multi-input and multi-output. Okay, so in most of the say all we have done so far is this part, single output, single input, single output. Okay. So later on in Math 3 or something that you learn with this one, the general. But let's do this one here. Because of the technicalities of functions, so output should be only one.
Sir?
Okay. Yes?
I think you haven't shared your screen yet.
Oh, sorry.
Thank you.
Where is that? Share. Right, so this is the picture. You have a system, single input and single output. You have a multiple input, one single output. You have a single input, multiple outputs, or you have the most complicated multi-input, multi-output. Okay. But because we want to express this system as functions, and function has the output as a function is a number. It's only not a number. Must be single, cannot be a multiple. Otherwise, it's not a function. Okay, so this tells you that, well, let's take this to be a factor. So the output is a factor. Instead of say 3 outputs, we say that the output is a single, but a single factor. So it has 3 components. Okay, so what we have now is this is t, this is x, y, z. Okay, so the object with the parametric equations is what we call a this is called f. This is a factor valued functions. Okay, so that's what we call a factor valued functions. domain E, usually described as this one. So T to the vector x, y, z. While x at t, y t, and z t uh, is a regular functions. Means uh, real real valued functions. So, example, um, you may have just three like this, or just two, or even more. Okay, so it's factor valued functions. Let's give you an example. So f of t here is say cosine t sine t squared, or t in the domain say 0 to 2 pi. Okay, so this is a factor valued functions, or t of t this is just e of t sine of t. Okay, and t from say 0 to 1. Okay, so this is factor valued functions. Okay, so given uh, given a function, factor valued functions, uh, find domain. Find its natural domain. Natural, what's this? Natural means the largest possible domain. Okay. So for example, alpha of t is a function defined by, say, 1 minus t squared. Here you have ln of t, and you have e of t. So find its natural domain. All right. So from the first one, you say this t must be less equals to 1, at most 1. So from here, you need t positive. Here, you don't have any restrictions here. Okay. So this is the x, y, and z. Okay. So the natural domain would be the intersection of the domain of x, domain of y, domain of z. So domain of x, domain of y, and domain of z. That is the least of this. Right, so t uh, t positive, but less equals 1. Okay, so that's t positive. Okay, so that is the this interval. Okay, so that's what's called natural domain. Okay. Now, the graph is difficult to, or say almost impossible to draw the graph because uh, here, for example, you need four things to describe because you have X, Y, Z, and you have T. So there's no way you can describe the graph of the functions. Okay, but you can graph the, say, the path. Consider this as a path. Okay, consider that as a path of a particle, say a moving particle. Okay. So let's do this one here. What about the calculus? Calculus of vector valued functions. Well, uh, it's no more difficult than the real valued functions, only you do this multiple times. Okay, so you have three components, then you have to do this three times as much as the real valued functions. Okay, so uh, here you have to think about in terms of difficulties, complexity, it's no more difficult than uh, real functions. Okay, but in terms of the work that to do, you have to do is three times or n times as much. Okay. All right. So first, about the limit. Uh, that f t is, say, three, okay, some domain. Okay. Then we say the limit, and say a is b. Okay. So this limit, what does it mean? This limit. This limit means of x of t, y of t, means that you compute each limit. Limit t equal to a and z of t. Okay. So, for example, this limit uh, of this function here. Uh, x, y. All right. Well, meaning that you compute each one of these. Okay, so each one limit of this. The square limit. Sorry, this is t, no x. T. Okay, so this is 1, this is 0, and this is also 0. Okay, so that's the limit. Okay, so nothing different from real valued functions limit. Okay, only you do this 3 times as many. Okay, so we say that the uh, calculus operations, that is limit, derivative, and integral on vector valued functions are done component wise. So for each component, okay, separately. Okay, so for example, you dt of sine t a, sorry, t square as a ln of t, and then e to the cosine t, for example. Well, you compute this for each derivative for each a component. Okay, so sine becomes cosine. The derivative of t squared times ln of t, so that means 2t times ln of t, plus t squared times derivative of ln of t, which is just t. And this gives you uh, negative sine t e to the cosine. Okay. Similarly, if you do integration from 0 to say 1, yes, that's the same as uh, integral of each one. So sine become negative cosine, this become 1 minus cosine t. Here you have 1/2 t cubed and 1/4, 3/4. Yeah, this is 1/2 plus 3/4. All right, get stuck again. 1/2, 1/4, 3/4. And here's a tangent 1. Okay, so it is no more difficult than for real valued functions, but you work 3 times as much. Okay, questions? Now in mechanics, f of t describes a positions of a particle f prime. This is velocity vector. It's a position as a vector, and second derivative double prime describe the accelerations of the particle. Okay, so these described as a vector value function. So we actually did some problems regarding this, but we didn't call factor valued function at the time. Okay, but we now formalize this in terms of factor valued functions. So let's do this one here. Okay, this 23. Okay, so the factor R of t is a precision factor. Okay, in 3 space at time t. All right, so find the velocity factor and the acceleration factor. That means the first derivative and second derivatives. So R prime and R double prime. And then compute the speed, no, not the velocity, the speed and the what's it, direction of the particle at time t. So what you need to compute here is that is from here you need to find first, okay, and then you need to find what is the tangent. The tangent is this one also. Tangent factor. Like you, all right. Like you mean the speed. Let me just finish this one. All right, let's do this one. RT. Plus 1, square plus 1, and 2t. Okay. Example. Given the motion of a particle is described as t is t plus 1, and then t squared plus 1, and 2t. You need to find the speed and directions at t equals 1. Okay, here so you have the velocity is r prime. So just 1 to t and then 2. Okay, so at time 1, this is just 1, 2, 2. So the speed is the length of this, which is 1 square plus 2 square plus 2 square, which is, let's see, this is 449, so it's 3. Okay, and the direction of the motions is actually the motion is actually this vector, the velocity vector. Okay, so that's one example. Let's see, there's another one. Um, see, given this one, let's see, where is that capture thing? Okay, so position is described as this vector value functions. Oh, okay. And you have a curve. Okay. Curve described as this one parametrically. Described parametrically as x to t squared minus 1, yt is 4, sorry, 4 minus t, and z is tq. Okay, and you need to find the parametric equations of a tangent curve. Okay, so you have a tangent, for example, here. Suppose this is a particle moving this direction. So you have a tangent there. Okay, so what you need here is to find the equations, parametric equation for this line, tangent line. Okay, so what we need here is point and a directions. Okay, what is the point? Well, the point is here at this point. Okay, so it's given 7, 8, negative 8. Okay, these directions. Well, the direction is, well, suppose this describe f of t. Okay, so this direction is f prime of t. So that's the tangent direction of a tangent line. So if you compute here, is that f prime of t is just that's 2t squared, so 4t minus 4 and 3t squared. And at time 7, let's see, what time is this one here? So we need to find t equals what? Okay, so here you get, well, let's see, t cube equals -8, so t must be -2. So from here, okay, so this gives you t -2, right? So check here, plug in t is -2 to y. So this should be 8. Okay, so let's match. Okay, all right, so that's t -2, 2, so this is -8, -4, and t squared 4 this 12. Okay, so parametric equation for the tangent line is, what is this? 7 minus 8t, 8 from here, minus 4t, and let's see, sorry, plus 12t. Okay, that's the parametric equation for the tangent line. All right, questions? Oops, 5-9. So I'll stop here. And we'll continue this at tomorrow. Okay, thank you. I'll see you then tomorrow. Stop to share and stop record.